merchandise manager, the merch manager, and I did bring my merch tonight. We did have a slide, but we decided not to show it this time, so you'll have to come next month to see the slide. No, you don't. Oh, no, there it is. All right. Oh, good job back there. And so you can see some of the items that I have. And like I said, I still have some of the boxes here. And let's see, on behalf of the secretary, I just want to let the members know that there's boxes here, index boxes that have name tags in them. So you can take a look and see if the name tag is spelled right for your name. And let's see what else. If you have any questions about merch, my merch email is merch, M-E-R-C-H, and then manager, M-G-R, at SBAU.org. So if you have any questions or requests, let me know. Back to you, Jerry.
Thank you, Pat. Now, our webmaster is not here, but he's set everything up, and I see it's running very smoothly. We'll tell him we have lots of problems without him. We're next going to go to, is our new secretary, Mike, is he here?
Yes, back here.
Oh, okay, good. Everybody turn around and see who it is.
Well, I don't have much to report tonight, because this is only my second day on the job. But I do want to say thanks to Tessa, who spent a couple hours with me trying to teach me how to do this. Pat, for her 3 2.5-inch 3-ring binders, a few 32-gigabyte flash drives, and her 18-page manual on Insider's Guide to Doing SBAU Secretary Duties. So I really appreciate that. And for Andy, is Andy here? No. But he helped me get into the website.
Okay.
So, thanks.
Thank you. When I was on the semester system, I always liked the first day of class because there's nothing due. And then I moved to a university that had the quarter system. And I had to learn very quickly that the first day of school of the new quarter, you had to assume you were 2 weeks behind. So anyway, thank you, Mike. Now we're going to go into our outreach, sponsored and organized by Chuck McPartland.
Okay, I'm going to take a little extra time. Thank you, Jerry. I'm going to take a little extra time this month. Sorry about that, because we have outreach pins for folks who did 6 or more, attended at 6 or more outreaches. At 6 or more outreaches 30 years. So anyway, what we usually do is just what's coming up this month. So it's fairly quiet till the end of the month. We have our Star Party here at the museum on the 10th, second Saturday. Telescope Tuesday has moved from the second Tuesday, or from the first Tuesday of the month to the third Tuesday of the month, so we won't be out there on the 6th. Instead, we'll have Telescope Tuesday on the 20th, Tuesday the 20th. We shift Telescope Tuesday each year to try to get the most near first quarter moons from Camino Real Marketplace because there's so much light out there. So that lets us have something to look at. And although the sea stars are pretty fancy, they can pull stuff out of that. And then on the third Friday is our regular monthly public telescope night at Westmont. And there's a cool event at Westmont this year, or this month, in that there's a large asteroid called Camilla that's going to be occulting a star, and the star is going to vanish for about 20 seconds. And it also has two or three known moons. I think it's 2 moons. It's a triple body system. And they might occult, although that's that's really more of an iffy. But Camilla will definitely, from our point of view, occult unless it's more elongated than they think it happens to be pointed the wrong way. But anyway, we'll be set up to show that.
What time is that?
That happens at 7:35. But I think the official start time for Westmont this month is like 5 p.m. So, or 6 p.m. So it's pretty early. Gets dark fast. On Thursday the 22nd, we have Roosevelt School for their science night. We haven't been there for several years, since before COVID. And I think they're having it set up in their blacktop, kind of in the back uphill from their main buildings. And then on Friday the 23rd, Fusion School has us setting up at Shoreline Park, kind of on the eastern edge, for their kids and families. And then on the 27th at Santa Barbara Junior High School for their science night, or their astronomy night, we set up behind the Marjorie Theater out there on their campus. So that's our outreach for there. Then, as far as the outreach report for the year, we had 198 scheduled events, although not all of them happened because of rain and clouds and smoke. Our attendance was 16,591 members of the public. Yeah. And that brings our total to 287,208 people since 2003. So we're past the moon, and we're still working toward 93 million. And that was roughly 2,800 volunteer hours, although that's undercounted because we don't count drive time and things like that. So a lot of people donating a lot of time to do that. And I have pins each year. We're part of the NASA JPL Night Sky Network, and people who help out at outreach for 6 events or more get a little pin that they can stick wherever they like it. And I've given a bunch out already, but there's people here that need them. There's Ronnie, you get one.
Oh my God, really?
Yeah. And this year they feature a lunar eclipse because there's a lunar eclipse in March. I don't think we're going to do a public event for it because it's at like 3 a.m. But there's another partial, I think, in July or August, so we might do something for that. Okay, Pat and Jerry. Sez and Tom are in Michigan. Ruben's not here. Marlon and Bruce. Bruce passed away on the 18th. I don't know if everybody knows that, but he's one of our regular members. Chuck Watson. Didn't see him. Isla's not here. Andy, Andre, Art Harris. Michael Robertson. Hey, you got one. Okay, and Edgar's not here, right? No, okay. Brandy. Okay, oh, you're right next to Michael, so that'll be easy. Okay. Brian Green, Brian's not here. Diane. Yeah. Sean. Okay. Thank you. Okay. Javier's not here. Chrissy's not here. Joe. Joe hates that, I'm sure. Greg, I know Greg's here. Greg Whitman. He was in the Planetarium show. Where'd he go?
Someone go back and search for him.
Yeah, maybe he's under the seat there, Beck. Okay. Sohini. Yay. I can give you all 3. Good. All those folks are sitting in a row. Thank you. Okay, and Charles Schuler isn't here, and Kim Kilster isn't here. So anyway, those are the folks that did 6 or more outreaches in the course of the year, and if you do that, you also get your membership extended for a year. So that's another nice thing besides getting a fancy little pin. So thank you. I'm sorry I took up more time.
Pat, the #1 volunteers, you and Pat.
Yes, I had a question about, do we not go out to Bacar's anymore? They don't like us, or?
Okay, so here's what happened with Bacara. So for 25 years, we've been going to Bukhara in the summer, usually every Thursday in June, July, and August, doing star parties for their guests. But we said we don't want them to charge, we want it to be for free. And they were happy with that, because the guests were happy. But every 2 years or so, the Bukhara changes hands, right? Somebody else buys it. And we have to reteach the new owners. Well, the latest group of owners called me up and said, hey, you know, we'd like to schedule outreaches, and we'd like to have them like every day. And I kind of, no, we can't do that. And I said, but we'll be glad to do the every Thursday. And they said, well, can you train our naturalists to do what you do? And I said, hey, your naturalist is welcome to come to any of our public events. And what they wanted to do was charge their guests. And so they're doing it now, and they're charging $95 per person.
Wow.
And from what I heard, they may have gotten better, but from what I heard, they basically have a person who hands out cell phones with apps on them for them to hold up to the sky and see what they're looking at. So, yeah. So I don't know if they'll want us back again, but you know, that's life.
I think we're out there in the garage.
Thank you, Jack. Okay, I guess we're down to the nitty-gritty. Let's do it. We've got the chaff out of the way.
Yeah, but I did, unless there's somebody else.
Diane. Oh, Diane, no.
She doesn't want to get nothing to say?
Yes.
Great job on the holiday party, though.
Okay, here's our Vice President in charge of speakers.
Thank you, sir, Mr. President. Jerry Wilson is the greatest president of the club. Tonight we're going to find out if our galaxy has been properly ionized or reionized, because we got a great speaker, and I'll introduce her to you in a couple minutes. But I need to, since I'm involved with people and booking, and incidentally, we got speakers coming and booked clear up through August. That's 2/3 of the year. I'll tell you in a minute here who the next 3 are going to be. If you want to see the whole 8 months up through August, go on our incredible website, which is run by the man who's not here, Tom Totten's back in Michigan with his mother. But that website, the latest guy I got, he's a big distinguished professor at UCLA, said, I went on your website and it's incredible. Never seen so much stuff on there. And I went on and I started seeing stuff. I wanted to pay tribute to some friends and people, and specifically, yeah, come on in. You're late. Don't let it happen again.
Actually, Ron, it starts at 7:30, so they're not late.
They're early.
They're early.
Like I said, the president told me it started at 7, and he proved it to me, he showed it to me. I'm not gonna get involved with that. I will say that Dr. Crystal Martin is here, we're gonna bring her on in a minute. I will also say right now, let's take our quick show of hands, just the newcomers, first timers only. You've never been here before, you're the ones we're gonna have to work on. In fact, the beer be bought by somebody. Dave Feinberg got his buddies. My good friend Mike Hardwick has his daughter and her whole family of 3 from Malaysia. And I think maybe raise your hand and people are gonna wanna talk to you. There you go. Thank you. I don't suppose Sean Kelly is here. Sean is here! There he is, teaches astronomy, professor at City College. And he has something in common with Mike. They've both done incredible in-house members-only speeches. We do that in December. So you guys that aren't members yet, you're here because of astronomy. You like to have fun. My professional opinion on astronomy is that it is the fun science of all of them. It gets more news than any other science except health and medicine. But we're more fun than that. And doggone it, if you join, you'll get to go to all these things. You know that 190 events a year is more than half of the year? Isn't it the year? No, it's 330, so it's a little less than half. So we're out almost half the nights of the month. It's just amazing. I also wanted to introduce last month's speakers. One of them, man that really became a hit at our holiday meal. Sitting over there, Dave Grossman, would you raise your hand? Matt Hall was the other one, is he here? No. Matt didn't make it, all right. Welcome, gentlemen. Thank you. Games are about to begin. Let me tell you who's coming, and then I'll bring on. Oh, I just want to say quickly that our weekly show on YouTube, which is Monday mornings at 11, we're about to start our 6th year, right? We've done 4.5. That means we're wrapping up the 5th. March 1st will be the beginning of the 6th year. And we've almost never missed a Monday morning. It's put together by President Jerry, who becomes a professor, and it's like doing a lesson plan every week with no vacation. But he does it, he loves it. We lost one of our 6 talking heads on the screen a couple of weeks ago, as Chuck mentioned. One of our stalwart, a good friend of mine, and then he's gonna be missed, Bruce Murdoch, happened to be president of the local theater organ society, passed away. And he was a loving man and a good man, and that's about the extent of our eulogy for him, that he's gonna be missed. We'll let you know, I guess, those of you members only, raise your hand. I wanna hear, that's most of us, yeah. Okay, you guys, get your pins. You can also, if you join the club, get one of these every time you come to a meeting. Yeah. Coming attractions, February 6th, month away, Joaquin Becerra Espinoza. Rising star, young UCSB grad student recommended to me by retired Professor Omer Blade, or Blade, B-L-A-E-S, I'm not sure how it's pronounced, but he used to give us great speeches. And he recommended Joaquin, going to talk about dark matter under the gravitational lens. March 6th, 2 months away, Dr. Rosalie Lopez, L-O-P-E-S, JPL, expert on planetary volcanism. On her talk, where the hot stuff is, volcanoes on the Earth and the solar system. And just confirmed this past week, April 3rd, I've been working on him. One of the few that I just picked his name out of the list on the UCLA faculty roster on Google. And doggone, he said, you know, I might like to come up there. I love your town. It's so easy to get people to come here live. Face it, we were Salinas. We were on Poker Bakersfield. Never mind, I'll probably get people from there. Dr. Matthew Malkin, distinguished UCLA Professor of Astronomy. We'll talk about what's new with JWST, the James Webb Space Telescope. The astronomy revolution is now. And we're working on getting Mike Brown, the man behind the Pluto demotion, but he's talking about other things, and he's working with the Vera Rubin telescope through the spring, but I'll be getting him in the fall. So we're about to get a full house on a rainy night. Cosmic Dawn, when galaxies, like many of us, were young. Everything's got to die, even galaxies. Featuring UC Santa Barbara Professor of Physics, Dr. Crystal Martin. The lady earned her PhD at the University of Arizona, folks. She won a prestigious Hubble Fellowship, which she took to the Space Telescope Science Institute in Baltimore. Held down a Sherman Fairchild Fellowship at Caltech for a few years. Then joined the faculty at UCSB. 23 years she's been out there. Our group out there focuses on how hot massive stars interact with their surroundings, a process called galactic feedback. They do thank NASA, the National Science Foundation, the Packard Foundation, and the Sloan Foundation for their support. Ladies and gentlemen, please welcome Professor Crystal Martin.
I think so. I'll get the lights.
Oh, great, thanks.
You want the one right over here, right?
Yeah, A, C, and D.
How's the sound? Can I
Good.
leave the mic here? It's good?
Yeah, sounds good.
All right, great. All right, so we're going to talk about James Webb Space Telescope today. Most people are kind of familiar with the idea even though you don't look at the sun, right, because you hurt your eyes. If you were to look at the sun with a solar filter, right, you see the sun as it was, not this instant, but 8 minutes ago, right? Because it takes 8 minutes, right, for that light to get from the sun to us. The thing about other galaxies is that they're so far away, it can take billions of years for that light to get to us. So in some sense, right, the universe is so large that it really does give us a way to see the past. Because the light left the galaxies a very long time ago, so we see those galaxies as they were a very long time ago. Not 8 minutes ago, but maybe actually billions of years ago. And that's the technique that we're going to employ today, okay? To learn to look at very distant galaxies, and by looking at very distant galaxies, learn what galaxies were like a very long time ago. So, you might be on the side of the coin that, okay, that seems obvious, fine, good, let's go. But if you start to think about it, that's actually like really strange that galaxies have a beginning and an end, or that the universe, right, has a beginning and an end. Right? This was something that actually really bothered Einstein, because on large scale spatially, right, one corner of the universe is just like another. If you go to a large enough scale and average over things, the density in this part of the universe, the density in that part of the universe, the temperature, everything's the same. It may even be infinite in extent, but statistically one part's just like the other. So it's very odd, actually, that the time coordinate, the temporal part, seems to have a beginning and an end. We're not going to answer that question today or really talk about it any further, but it's nice to pause for a minute and think. Just the fact that we're going to talk about the evolution of galaxies and that they have a beginning and a future and an end is actually not so obvious that it's a question we can even ask. So, cosmic dawn is what we're going to talk about, visiting a time when galaxies were young. So before we go there directly by looking at distant galaxies and seeing them as they were a long time ago, let's start out and look at the archaeological record. Okay, that came from. This is looking at the center of the Milky Way galaxy, okay, from our vantage point out in this. You know, one of the morphological features of the Milky Way is this bulge in the middle, this big sphere, right, of stars. And that's the oldest part, okay, of the galaxy. Talk about how we know that in a second here, okay, but that bulge is the oldest part. You see lanes of dust in there, okay, and a disk. That disk is the young part, okay, of the galaxy. Some parts of that bulge, the globular clusters, probably a popular target. This is M94, okay? Perhaps you've looked at it in a telescope. That dense cluster of stars is close to 14 billion. That's billion with a B, okay? Close to 14 billion years old, not 13.8 billion years. So that's one of the oldest parts of the galaxy. I think it was kind of there first, a system of star clusters, whereas some of the stars in the disk, many of those stars are hundreds of millions of years old. Some of the youngest regions, we'll go look at in a minute, are literally just millions of years old. So, as astronomers, right, how do we know about these ages? And it comes down to stars and how stars are held up, okay, by thermal pressure on the inside against gravity trying to pull them together. And it means that in this called the Hertzsprung-Russell diagram, which if you ever took Astronomy 1, you've seen, but this is a simple idea. where from left to right here, we're looking at temperature. When this is a hot star, and this is a cooler star. Okay, so hot to cold. And then we're going faint to bright, okay, on the y-axis. So most stars lie along this track here, we call the main sequence of stars. And that's kind of the only place physics lets stars lie for a long period of time, okay, when they're balanced by the hydrostatic equilibrium between gravity fighting pressure and powered by nuclear fusion, and the radiation is leaking its way out, slowly diffusing. This is kind of like the only place they can end up and be stable. Okay, so they all lie along this track. And astronomers use, okay, these properties of stars extensively to understand the history of galaxies. Okay, this is our tool. Because along this sequence, from the hot stars up here in the upper left to the cool stars down here with, you recognize the sun? Hot sun, right? A G star, here at 1 solar luminosity, right here in the middle. Okay, there's the sun. We got stars that are 1/10 the mass of the sun. We've got stars up here that are 100 times the mass of the sun. But as those masses change, we see the temperatures change. And you can see here that for the hotter stars, the luminosities go up from a solar luminosity to, that's 10,000 solar luminosities. So this relation is critical for how we learn about the ages of the stars in other galaxies, because they come from these colors. And what you see here is that a blue star that's very luminous, that's a single star. A single star that's maybe 100 times the mass of the sun, but 10,000 times its luminosity, means it has a very short life. I mean, the sun now is about 4.5 billion years old. Some of these O-type stars will only live for a few million years. Right? We're talking masses 100 times higher, so 100 times more fuel. But a luminosity, it's 10,000 times higher, so it's using up that fuel much more quickly. So when we look at distant galaxies, when we see light that's dominated by these O and B stars, we know those are stars that formed very recently, i.e. within the last few million years, okay? Recently. As opposed to one of these K or M stars, 1/10, 2/10 the mass of the sun, they have lifetimes that any of them that have formed are still around. The universe isn't old enough for them to use up their fuel because they shine at such a low rate, okay? They're very slow here. So I said there were regions of the galaxy, right, that were young here. Let's zoom in here. We look down here at the Carina Nebula. We've got a bunch of red light here. This is emission coming out from hydrogen atoms that are blowing, because this word we're going to use about ionization of the universe. Here we're talking about ionization of a star-forming region. Let's start, okay, in a galaxy locally, and where there's a massive O or B star, some of that radiation coming off is in the ultraviolet, in the far ultraviolet, where it can rip electrons off of hydrogen and helium atoms, okay? And that hydrogen and helium gas blows, okay, once the electrons have been ripped off. Just the electrons get ripped off, and then they go and they find another ion somewhere, and they recombine, and then that releases energy, and we get this glow. Okay? So in galaxies that are clear across the universe, we will see light from stars, and we will see light from emission lines, that is this glowing gas, okay, if there are young stars there. And that'll be a key diagnostic that we'll need. If we zoom in on the Carina Nebulae, you can see shells and filaments and things. Again, the glowing light is the ionizing radiation, okay, coming off of the young stars, and ionizing the gas that's recombining. And the shells are coming from stellar winds and supernovae that are imparting mechanical energy, okay, into the gas and blowing it apart. So star formation can be a destructive process at some level. Okay, so that's the archaeological picture. Let's take a look now, this idea of light travel time and looking back in time by looking at distant objects. And this is the scale that we've got to work with, okay? Where I'm gonna define something called redshift in a minute, okay? A term you've heard, but we'll define it. And we're looking here now at how look back time to a galaxy or some object at a particular redshift, okay, changes. So you can see here at a redshift of 10 to the 0 is 1, you're looking back in time about 2 billion years. Not bad. Okay, but 2 billion years ago, well, that's a time scale you're familiar with, right? Who's hiked down to the bottom of the Grand Canyon? Right, okay, right? You're getting down there to rocks that are a couple billion years old, so that part of the Earth was forming, okay, when light was leaving these galaxies that are at redshift 2. The light's been traveling across space that long to get to us, okay? Like, wow. But look here, this time scale, okay, as we go back towards redshifts of 10 here, right, we're getting up to time scales of like 13 billion years, and the Earth, the sun, they weren't around then, okay? Well, the Earth, the sun, right, they're in that disk of the Milky Way galaxy, which is the young part, okay? We're looking back in time here to other galaxies when the only part of the Milky Way that existed were these globular clusters, okay, in the bulge. And you can see here, right, as you get up to kind of the age of the universe, which our best estimates right now are about 13.8 billion years. This quantity redshift, this is a logarithmic scale here, right? It's getting up to 20, 30 or so, and then it's turning over and running out. So why do I want to introduce this term redshift, okay, and talk about time in terms of redshift? And it's because when we look at a distant galaxy, it doesn't have a neon sign on it flashing saying, I emitted my light 10 billion years ago. It has a flashing neon sign that says, I'm at redshift 6, or I'm at redshift 5. So let's take a look at what that sign is. Okay. So this is the best illustration of the concept of redshift. I'm going to take a balloon here, wish I had one with me, and then take a hole punch and get a few little circles of construction paper, paste them on the balloon. I like the circles of construction paper because we blow up the balloon and the universe expands, okay? The universe is the surface of the balloon. The galaxies don't expand, right? They're little pieces of construction paper. Just like as the universe expands, a galaxy is held together by gravity, and it's not, we're not expanding, right? As the universe expands, we're held together by electrostatic forces, okay? But the individual galaxies, every point on that balloon, as it gets bigger and bigger, moves away from every other point. And a galaxy that's twice as far away, if this galaxy is twice as far from that one as this one, as it expands, right, there's more space to expand, and everything grows proportional to the separation of the objects. Okay. So redshift is just defined here, so that 1 plus the redshift z is equal to the change in the scale factor. And we define the scale factor r at t0 now to be 1, and we can think of that as being a scale of the universe, a radius, a size, and the scale factor at some other time is just given by the redshift, okay? So if we say redshift 1, we get 1 plus 1 on the left-hand side there is 2, okay? And that's equivalent to a change in the scale factor of a factor of 2. So if we say the scale factor is 1 now, then the scale factor is a half at redshift 1, okay? Inverse that. So we're going to be talking about observations that we made of galaxies at redshift 7. And you can see in that sense, that's going pretty far back in time. It's going back to when the scale of the universe was like an 8, okay, of what it is now. Now, the other key thing here about redshift is that it's not just the distance between galaxies that stretch, but if this is a photon, okay, a wave traveling across the universe, as that space stretches, the wave stretches. So this means that the observed wavelength of a photon that's emitted at some wavelength, it gets stretched out by a factor of 1 plus the redshift. It's simple because it's just the same stretching as the scale factor of the universe. So for looking at distant galaxies, which is what the James Webb Space Telescope was designed to do, this stretching of the visible photons emitted by stars into longer wavelengths shifts them into heat, into the infrared part of the spectrum. And that's what drives, okay, the design of the James Webb Space Telescope. This is a segmented mirror, okay? That's so that it can be made to a perfect surface with thin segments and made large, because we're going to need to collect a lot of photons from these different objects. But it looks golden, right? It doesn't look like aluminum, and it is golden. And that's because of this redshifting of the photons, because we want to detect infrared light. And gold is very reflective, okay, at infrared wavelengths. We've got a gold-plated mirror here. And the Earth's atmosphere, right, is also excellent at both trapping infrared heat and blocking infrared light from getting in, so we need to launch it in a rocket and put it up in orbit, okay, so that we can see through the Earth's atmosphere there. Okay. So JWST is optimized, okay, for this. So let's see how we can use it, okay, to study the emergence of really the first galaxies, okay, in the universe. So here we've got a plot where time here, okay, goes from left to right. So think of this as early in the universe, before there were any stars. So in the top panel here, we've got a simulation. And what's the universe made out of? Well, it's made out of mainly dark matter and dark energy that we don't know what they are, except that they're not normal baryonic material like we're made out of. This is a theoretical simulation. Just call it the dark matter, okay? And as the universe expands, the matter becomes more and more diluted. It's like ordinary matter in the sense that you make the volume bigger and the density goes down, and that's what you see happening in the matter distribution, okay, from left to right here. The universe is expanding, the simulation's being rescaled to kind of keep it all in the same box, but you can see the density dropping. And then what we want to visualize in the bottom panel is some prescription of star formation, okay? So like a density threshold, where if the density gets high enough, the gas will start to collapse and make stars. And this is a simulation of prediction for as a function of time then. We're seeing not quite star formation, but we're using the density here to predict stars forming. And then we're following the ultraviolet light from those young stars, the O and the B stars. And in yellow, we're seeing the region around the O and the B stars that are like the Carina Nebulae that I showed you, right? In the Carina Nebulae, there was a red region around the O and B stars, where the ultraviolet photons were ionizing the atoms. Ionization just means taking the electrons off from the outer layer of the atoms, okay? So bathing the atoms in ultraviolet light, and you see basically little regions around, individual clusters, and the little regions around individual galaxies. And then by redshift 5 here, okay, at the end, basically the whole intergalactic medium, all the space between the galaxies, the hydrogen gas that's there is completely ionized. It's not hydrogen, it's a proton and an electron, okay? Because there's enough photons in the universe to take every atom apart into its nucleus and its electrons. So that's important because when we look through the universe, it's hard to look through a gas that's still neutral. It tends to absorb photons. So the intergalactic medium today is very transparent in part, okay, because it's ionized. So we can look at this another way and say if we could measure the ionization state of this intergalactic gas, and if we could look back and find times where it wasn't fully ionized and find these little pockets of gas, we would be looking back and finding some of the first galaxies. So the project that we'll be talking about is how to use, okay, looking for ionized gas in the early universe to find the first galaxies and vice versa. Now, an interesting thing is that astronomers will call this process re-ionization. With the emergence of galaxies, the emergence of stars in galaxies produce ultraviolet photons, and then the ultraviolet photons ionize the gas. Okay, that's ionization. What are we re-ionizing? What are we re-ionizing? Well, so what I just described is kind of the bottom panel here, where it says first stars, first galaxies, and then the neutral medium in blue is giving way to this dark ionized medium, and you see galaxies emerging. This CMB stands for cosmic microwave background, and the top panel there just goes to the left here that precedes this cosmic microwave background. So time is going this way. Okay, this is a time when the universe was quite young, about 300,000 years old. That's pretty young compared to 13.8 billion years today. And the top panel then shows in that first 380,000 years, starting from the Big Bang and going through basically a time when the universe was so dense that the first photons and baryonic particles hadn't made atoms yet, okay? So we start out with a hot Big Bang, and then as the universe expands, it is cooling off. When it's a few minutes old, see this is 100 seconds there, we have an epoch of cosmic nucleosynthesis, when the universe has cooled off enough, okay, for the quarks to make nuclei. And then as it cools off some more, okay, we basically eventually get to the point where atoms can form. So the very, very early universe was already ionized because it was so hot. And when we get to about 380,000 years, we cool off enough to make atoms, and then the universe meets this cosmic microwave background. Okay, so here's back to the Thiessen simulation again. And this is showing a picture. Zoom in here, there we go. In one of the regions there of how the galaxy might be forming in a little region. These are filaments of gas feeding the galaxy. And then this is a picture of the ionizing radiation ripping the electrons off the atoms, okay, around it. And we were particularly interested in trying to learn of how this process proceeds, okay? It's kind of two competing pictures, one where the ionization starts in the most dense regions first, another picture where it starts in the least dense regions first. Try to take a look at that. Okay. So I show quickly here, just again, the concept of ionization, because that's central to what we're going to talk about. This is the Bohr model of the hydrogen atom. Might have seen that before. The idea is that's a nucleus, okay, in blue in the center. So that's the proton of a hydrogen atom. And that's a picture where an electron, the single electron, is going around in an orbit. Okay, kind of like planets in the solar system. And what you need to understand for this talk and the spectral lines that we're going to talk about is that electron can't orbit just anywhere. And we can think of it as having kind of discrete orbits, and as it changes from one orbit to another, those orbits have different energies. So if we picture the electron in red there, being in the innermost orbit, think of that as the lowest energy state. And if we add energy to the atom, that electron could move up to the next orbit. And if we added even more energy, it could go up to the next orbit. And so on, where the ionization energy is the quantity called 1 Rydberg, 13.6 electron volts that's needed to unbind it from the proton. Okay. So the universe is mostly made, in terms of the baryonic material, it's mostly hydrogen, okay, with about 10% helium by number. So photons that can be absorbed by this hydrogen atom can't travel very far through a neutral medium. And that's what makes it possible to probe this transition from a neutral medium to an ionized medium. When the neutral medium between the galaxies is has the electron bound, it will stop the photons that are at the resonant wavelengths, okay, of these atoms, so they won't travel far. So one way to find the regions, okay, where the hydrogen atom is emitting is the Lyman alpha line. So when that electron in red there, when it transitions from the first orbit to the second orbit, back and forth, that amount of energy from the first to the second level corresponds to a particular spectral line. Okay, it's in the ultraviolet part of the spectrum called the Lyman alpha line. And that is a way to, you can imagine, since most of the gas in a galaxy is hydrogen, and since this is the transition from the lowest energy level to the next highest one, this is the brightest spectral line you can get from a galaxy. So it's used, okay, to pick out distant galaxies. So now this is a map, okay, on a scale here of degrees 3 scales. Okay, so we're looking at a patch of sky here, not so different from the size of the full moon, okay, on the sky. So this was a large ground-based survey that was done to pick out Lyman Alpha emission, basically at redshift 7. So these are very distant galaxies. So these are going to be our targets that we're going to look at with the James Webb Space Telescope. And they're known to emit, okay, in this Lyman Alpha line. And what we're going to be doing with James Webb is looking at another spectral line that corresponds to the electron moving from the 2nd orbit to the 3rd orbit. And that's a rest frame optical line, so it goes through ionized gas, whereas the Lyman Alpha line won't. So we're going to use the James Webb, okay, to basically look at this other hydrogen line that will tell us how many of these Lyman Alpha photons were actually intrinsically emitted, and then use the number that we measure to see how many the intergalactic medium basically absorbed, okay, and took out of the picture.
Where did the energy come from to cause the electron to move to different levels?
Yeah. Probably from a star nearby. When we looked at the Carina Nebulae, we saw in red the glowing gas around it. So here, right, these atoms are in a galaxy, and you're not going to have Lyman Alpha coming from the galaxy until you form some massive stars in it.
So it might have had to be a very first star somewhere a zillion years ago.
Yeah, so here we're finding, we're picking out the subset of galaxies at redshift 7 that have massive stars in them.
Well, and then with James Webb, they've also found that there are galaxies that out there that appear to be older than you would expect. The Big Bang concept is further out you get, the earlier the universe, but they found things that don't seem to fit that long. How does
Yes.
that play into this?
They haven't found any galaxies with James Webb that are more than 13.8 billion years old.
Is that right? So everything's holding up in terms of what they're seeing.
There's no problem with the age of the universe at the moment.
Okay.
There's lots of problems, but I don't think we can. Let's go find some of the problems. So, our goal with James Webb, okay, we've got this Lyman Alpha measurement. We need to measure the hydrogen alpha line to compare it, okay, and then we're going to figure out how much of the Lyman alpha is leaking through. So we take a spectrum of the galaxies, which means we've got to find their position very accurately. So we first image the field. It shows an image there. And then we got our Lyman alpha spectra here. This is an example of starlight from a galaxy, and then that's the Lyman alpha spectral line, right? You can see how it's very bright. We can obtain those from the ground at Keck because it's closer. But then what will happen, right, if we picture this as a galaxy here, in blue is a picture of a Lyman alpha photon. It just has a very small pathway that it can traverse through space without hitting a neutral atom in the galaxy or around the galaxy and scattering in some random direction. So you can see here one, so that at 7 o'clock there, that's scattered many times and then leaked out. But at 10 o'clock, right, you see a Lyman alpha photon that's scattered a few times, and then it hits a dust grain. Oh. Remember that picture of the Milky Way we started with? And in the disk, there was all that dust. Well, it's kind of inherent that galaxies are going to be dusty places, right? Because we got a bunch of nuclear furnaces going on. And guess what? There's soot, okay? Things are dirty. And dust grains are solid particles. They're little silicates and carbonaceous grains. And when that Lyman alpha photon hits a dust grain, it's just absorbed as heat. It's gone. The photon is no more. So this is what we mean by some of the Lyman alpha photons, okay, not making it out. these are examples, okay, of how if we put a galaxy in a completely neutral intergalactic medium, the Lyman alpha line, when it leaks out of the galaxy, will kind of walk its way away from the resonance frequency and come out as two peaks. But then as it comes through the neutral intergalactic medium, it's basically all absorbed and nothing comes out. If we now put it in a ionized region, okay, H2 means ionized, a little bit of it will leak out. If we make it in a more ionized and a less dense region, we can get progressively more and more of the line coming out. Our goal is to kind of measure what the line, use the H alpha line from JWST to get the intrinsic amount of emission that should be there. Okay, so that model is going to give us how much is there. We compare it to what we see, and we'll know how much the line was attenuated. There's just another way of looking at those. And that will give us a transmission there. By comparing this Lyman alpha brightness to the H alpha brightness. And the 8.7 is just some quantum mechanics thrown in to get the predicted numbers. Right. Okay. So here's a rest frame optical spectrum. This is what we're going to be trying to get from a distant galaxy. And this H alpha line, okay, that we're after, okay, is this bright line right here. Okay, so how do we get it? So here is the beautiful, okay, imaging from the James Webb Space Telescope of our field. We're looking here, this is image at 1.5 microns. Okay. You see all these spikes coming off. It's from you saw in the segmented mirror, the mirrors were hexagonal segments, which is part of the point spread function, okay, of the telescope. And then the optics there, all point sources look like that. So things that are stars, you can see because they have those diffraction spikes on them. And then you see lots of other little galaxies. Every little dot here, right, is a galaxy. There's a nearby spiral galaxy. Let's zoom in on that. So this is probably like at redshift 1. You see the beautiful, I mean, you can just, it's been hours, it's been days just looking at these images. I mean, that galaxy's at redshift 1, you see a bulge in the middle, you can see spiral arms, you can see star-forming regions in the spiral arms, right? There's a beautiful edge-on galaxy with a bulge. You can dock at these for a very long time. There's a bulge and a disk there. These distant Lyman alpha emitting galaxies, there's two of them, and I'm going to zoom in here. One's in this little red box, and one's in the other little red box. You wouldn't even pick them out by eye. They're little dots here.
But the galaxies don't give us 6 spikes, do they?
Yeah, because they're not point sources. So essentially, every little point in the galaxy makes a 6-spiked pattern like that. But then they're all overlaid,
They're kind of buried.
so you don't see it. So it's buried.
Is that ultraviolet light or the sun?
This is an infrared image.
Infrared.
It's 1.5 microns.
What exposure was that?
This is about an hour. So we use these images, right, to get very precise locations for where the Lyman alpha emission was coming from. Because ultimately what we want to do, we'll zoom in on those, is to take a spectrum and get the infrared spectrum. We have to put a little box or an aperture. The spectrograph, it's like you look at the field of view, and there's like little doors all over it. And then you tell it which little doors to open on your object to let the light through and pass it to the grating to take the spectrum. So we have to center each object in a little box like that. And if we do it right, we get spectra. So here is an example. This is the same object in two different filters. This is at 1.5 microns, so that's rest frame UV light. This is at 4.4 microns, so this is the rest frame optical light. And the first thing we learned for this Lyman alpha emitter is look, there's two galaxies there. Or at least it looks like there's two galaxies, a bright one and a little faint companion. And you could say, well, but is that really two blobs in the same galaxy, or is that our target in a background galaxy? Well, so now we look at the spectrum. So picture that little red rectangle was the slit. Now the slit is the position here, and this direction is wavelength, or put it in a velocity scale. And you see the bright blob makes the top spectral line there, and the second little blob makes the second spectrum. So both of those blobs have the detection of a spectral line, and you can see they're basically at the same wavelength. So they're physically connected. There are two galaxies there. And this is a measurement of the hydrogen alpha spectral line. And this is the Lyman alpha line that we'll be comparing it to figure out how attenuated it is. So let's just go through a little rogues gallery here, okay? And look at some of the other galaxies. Oh, that's actually our aperture. So we had to work very hard to line up the direction of the slits to get the two clumps. Okay. So this is number 2, and look at the position of the Lyman alpha. Yeah, there's two galaxies again. There's two blobs there, and in the spectrum you can see that they're both emission lines at the same wavelength. Let's go to this one. There's two blobs there again. This time in the spectrum you only see one, but if you look at where the slit's placed, you see the slit is placed here, and the second blob, it's not in the slit. So this light doesn't go down the spectrograph. So in a separate exposure, we had the slit on this object, and it actually is at the same distance as well. So this seems to be a merger as well. So here's one that's single. Yeah,
What is the velocity?
where's the,
What is it? What's the velocity of?
this is velocity of, just think of it as wavelength. It's like the spectral line. So like, I put 0 at line center, and it's like redshift and blueshift. So you can see, in the Milky Way, right, the rotation speed's about 250 kilometers per second. We're talking about things that are a little less massive than Milky Way, but not so different. So very clumpy. Here's another one. And again, there's two spaced further apart. More clumps. So one of the real surprises here was just the number of beams that were multiple. Now, the name of the game of what we were trying to do here was to understand how large an ionized region had to be around each Lyman alpha emitter in order for the intergalactic gas that's still mainly neutral to transmit the Lyman alpha. And this is a model, okay, that we made here that for a given shift of the Lyman alpha emitter relative to the H alpha emitter, think about it, it's just the velocity offset, okay, for each one of these, you can measure, basically, you can model how big the bubble has to be, the radius of the ionized bubble around the galaxy, how big does it have to be to transmit a certain amount of the Lyman alpha emission, okay? So as the bubbles get bigger, you transmit more and more of the Lyman alpha flux. And then the shift here just shows you that if the line is kind of at the systemic velocity, the bubble's got to be quite a bit bigger than if the line had some Doppler shift, okay, to start with. So we measure which of these curves we're on by comparing the velocities of the Lyman alpha and the H alpha lines. So we know which curve we're on. And then we measure the transmission from comparing the Lyman alpha flux to the H alpha flux. So we've got a curve and we've got a transmission, and then you plot the galaxy there and you read off the size of the bubble around it. Okay? There are two sets of points there, solid and half field, and those are for two different assumptions about these sizes, okay, of the bubbles, the velocity offsets. So for the solid symbols that give the smaller radii, this is the picture we get. For each of those Lyman alpha emitters, the red sphere shows the region around it that's ionized. And what's interesting is they kind of fall into like three lumps, and then within each of those lumps, the bubbles are starting to overlap. So we're making quite a bit of progress here from individual galaxies with little ionized spheres around them toward, right, we're progressing in the direction of reionizing the whole intergalactic medium, where just all these bubbles overlap. And if we go to the example with the half-filled circles, these are kind of the two limiting cases. You can get to the point here where really the whole protocluster region, those bubbles are starting, okay, to overlap. So this is at redshift 7, and in this overdensity of Lyman alpha emitters, okay, a region that's today would be like the coma cluster, a very rich region of the universe. It seems to be ahead of the universe on average in terms of reionizing. So the overdense regions are more ionized, and the filling factor here of the ionized gas in blue is close to unity. In comparison, right, if at redshift 7 here, okay, we look at the neutral fraction, the fraction of the hydrogen that's ionized, on average in the universe here, right, that ionization fraction, well, it's transitioning rapidly at redshift 7. You can see from at higher redshift where the intergalactic gas is all neutral, and at redshifts below 6, basically there's no neutral gas left, it's all ionized, and oh, we're in this regime around redshift 7 where the transition is happening. This is the lights turning on in the universe, and the starlight leaking out of these early galaxies and reaching kind of every corner of the intergalactic medium. And this is that neutral fraction dropping, you can see between redshift 8 and 6 as it happens. At redshift 7, where this protocluster is, okay, in that protocluster, the neutral fraction is very small. It's about 0.2 or less. So our cluster is down here kind of at this end of the range, just showing that very rich pre-coma region is kind of a bit ahead, okay, of the universe as a whole. So, you know, the big surprise in this, I would say, is that these galaxies are mergers. And what role that has in the star formation histories of these galaxies and driving this reionization of the universe is an open question, but it would seem to have some in the modern universe today, right? Galaxy mergers kind of come in two flavors. We call them dry and wet. When spheroidal galaxies, like ellipticals, merge together, the spheroidal galaxies are big balls of stars and dark matter. There's no gas left in them. They're the old passive galaxies. And one ball of stars and another ball of stars slam together. Well, they don't actually slam together. There's enough space between the stars. They kind of go through each other, and then gravity pulls them back, and they oscillate, and they merge, and okay, that's it. But when two spiral galaxies, right, when the Milky Way and the Andromeda Galaxy cream into each other, because they have disks that are full of gas, and those gas particles, there's about 1 hydrogen atom per cubic centimeter in the interstellar gas in the Milky Way. Now, if you think about it, right, that's 1 cubic centimeter, 1 atom. That's macroscopic. That's enough that they're going to slam into each other. Now, of course, 1 atom per cubic centimeter is about 14 orders of magnitude a better vacuum than you can make in the laboratory, okay, on Earth. So it's a vacuum, but it's dense in its own way. So these spiral galaxies, M31, Andromeda, they go smack, while the stars kind of go through each other. The interstellar gas goes smack. That sends shock waves through the gas, which compress it even more, and new star formation is triggered. So that's why we call it a wet merger. It's got gas in it that triggers more star formation. So these early galaxies that are merging, they still have lots of gas left. Okay? So the merger is the collision will cause compression that will cause more star formation. And that's probably one reason that these galaxies are particularly effective at making ionized regions around them. Okay? So I want to open this up largely and take questions from you guys. There's lots more detail about this work. We can talk about it if you want. You can go to this website and download the paper. I want to give credit here to people that did a lot of the hard work in this, particularly Wade Hu and Isaac Wold, who were postdocs who were here at UC Santa Barbara and worked on this. Wade is now at Texas A&M, and Isaac is at Goddard Space Flight Center in Maryland. But they did a lot of the early work on the data. Oops. But you can read all about it there. And there are many more aspects of this in James Webb that we can talk about if you like, but I want to follow your questions.
You were there time, everybody.
Let's go.
It was great.
Aren't a lot of the galaxies much in the early fields much bigger than we expected? Can you comment on that?
A lot of the galaxies in the early field are actually quite compact.
Yeah.
The most surprising thing we've seen, something we call the little red dots, these guys. This is what we're all really scratching our heads about. So these are unresolved. They're the size of the point spread function, and they are extremely red. Even in the rest frame, there's not much ultraviolet light, which shows they have quite a bit of dust, and there's a lot of luminosity coming out. These are thought to be some sort of black hole, but their spectra are not like the black holes in the local universe. We're picturing them kind of as supermassive black holes that are surrounded by a dense cocoon of hydrogen, almost like the envelope of a star. So that the energy from the black, instead of a nuclear furnace inside a ball of hydrogen, you've got a gravitational furnace. And that supermassive black hole, then the energy is diffusing through this dense envelope. The very early universe, kind of redshifts 8 to about 14 now. We're finding these little red dots. And, you know, you need pretty massive black holes. And how you grew a black hole that big, that quickly is definitely surprising. The models at least did not predict it. There are certainly models that can post it. So these are very small, very small. Yeah.
Are there any 13-billion-year-old galaxies near us? Well,
Yeah.
there's the Milky Way. Are they all?
Right, right.
I mean, it seems like they're always very far away. I don't think we have any bit old ones.
There are near ones, there are near ones. So again, there is the disk galaxies, we said tended to be young, okay? So Andromeda's young. The spheroidal galaxies are the older ones. And there is a morphology density relation. You find the spheroidal galaxies, the elliptical galaxies, in richer environments, so in more dense environments. So we've got the Milky Way in a pretty poor group. There are also rich groups. But then locally, you know, we have massive clusters of galaxies, okay? The Virgo cluster is kind of, you know, the nearest big city, okay? But, you know, what's a good analogy here? You know, if we go all the way up to the Coma cluster, let's say either the center of Virgo or Coma, you're getting the structures that are big enough that there are galaxies there that, you know, a lot of the stars in them are of order 13.8 billion years. You know, even in the Milky Way, even though most of the stars are young, keep in mind that those globular clusters are, to, you know, the accuracy that we can measure it, consistent with the age of the universe. So there are parts of the Milky Way, a small part of the Milky Way mass, that does seem to be very old.
How old are they very old?
13.8 billion years.
That's old.
Yeah, yeah, within the error bars, the globular clusters are the age of the universe. Yeah.
What's the most pressing question you personally would like to find the answer to?
Oh, that's good. Yeah.
Is there a God out there? Gravitons.
I don't know, I mean, there's questions that I think can be answered, you know? Little
Yeah.
dots, okay? I'd probably say that in terms of like, you know, what I'd really like to know the answer to. I mean, I think I would be more theoretical actually and say, you know, to me, it's like very bizarre that this time coordinate, you know, seems to have a beginning to the universe. Whereas, you know, space is like the same in every direction. Why is the time coordinate so different from the spatial dimension? Why does our universe have time? What does that mean?
How old is the Milky Way?
How old is the Milky Way?
Right.
Depends what part of the Milky Way you're looking at. Most of the stars in the Milky Way are in the disk, where the sun is. That part of the Milky Way is about 4.5 billion years old. Okay? But those globular clusters are about 13.5, 13.8 billion years old. The Magellanic Clouds have star-forming regions in them, or even some of the regions in Orion that are only a few million years old. Where there's compression in spiral arms and new stars are forming. There's star-forming regions. So There's a large range of ages in the Milky Way. It's still quickly growing.
So most of this research that you're doing is with the James Webb, which is putting you way out in the early, theoretically, the early formation of the Big Bang or whatever. So you were, correct me if I'm wrong, you're basically studying what was going on with galaxy formation way back in the early times. Is that correct?
In this work, yeah.
In this work?
Yeah.
So you're finding, are you finding things that are different out there than, say, would be in closer, which would represent an older period, or?
Yeah, I mean,
Yeah.
the thing that's the most different are these little red dots. They don't seem to exist.
Oh, good.
A lot of the other things, you know, a lot of my career has actually been spent studying nearby galaxies, star-forming regions in nearby galaxies. I think it's amazing how similar the distant and the local universe are. You know, spectrally, you see the same lines, you see slight difference in densities, you see evolution in the chemical abundances, okay? There's more carbon and oxygen around in the local universe than there was at early times. But, you know, not by so much, right? It's like that end of the cosmic nucleosynthesis when the universe was 3 minutes old, okay? You made hydrogen, you turned about 25% of the mass into helium, and you made some trace amounts, okay, of carbon. But, you know, most of the carbon and oxygen in the universe has been made by stars more recently. But you add all that up, and it's still just, you know, 2% of the baryonic mass. So the universe is relatively uninvolved chemically. But you can see that difference, okay, today and in the past. But it's almost like more similar than it is different.
Maybe we're not going back far enough. Looking back far enough.
Maybe, yeah.
How long did it take you to assemble all that data?
To process like the observation or?
And collate them all with all the galaxies?
I mean, once the observations were done, and we just had the raw data to make nice pictures like this, we turned it around in about 2 weeks to get pictures. And again, Wade Who and Isaac Wolm, the three of us, we had to do it quickly. We had a special program where we got the imaging to get precise astrometry to make the mass and take the spectra. So we were on a timeline that we had to get our spectral designs turned in.
Where is Keck located?
Keck Observatory is on the summit of Mauna Kea in the Big Island, Hawaii.
For the data analysis and for the write-up of the article, that was more interesting. That was probably
Yeah, it took a
years.
couple of years, yeah.
Yes.
Yeah.
Okay, this has nothing to do with astronomy, but like on your credits, I saw 15 different institutions involved.
Yeah.
And I'm wondering, how do you coordinate that? Like, do you all say ahead of time, hey, you know, people want to work on this and everyone's doing a little piece? Or are different people doing different things, or?
Kind of all the above. I mean, one thing is that Zoom is wonderful, okay? We spend a lot of time on Zoom. And usually people take different roles, okay? You know, a few of us work more on data reduction, a few of us work more on the theoretical modeling side. Whoever the lead author is of the paper kind of organizes people to pull parts together.
Because the impression of science is always that, like, there's this competition to be the first to publish. And so you have to get everybody, like, in agreement somehow to,
It's like any other team, right? You gotta work together if you're gonna publish before the other teams do.
okay. So there's another 15 institutions doing,
Yeah, I mean,
Okay.
these data are all publicly available now, so,
Okay.
yeah.
So this is the first time that I see what a single sub exposure from the James Webb looks like, and I'm just curious on how they assign color to false color images from the James Webb, because the process image that I've seen, they all have color.
Yeah. That's a great question. You know, here, right, I've chosen a grayscale to just show intensity. Some color maps just show intensity, okay, with color. Sometimes, though, a color image is made out of like, almost like on a screen where there's like a red, a green, and a blue, you know, video tube. In these images, you might have noticed they're in pairs, where this is a 1.5 micron image and a 4.4 micron image. If I added to this a ground-based image at 0.814, then I could assign that blue, assign this green, and assign this red, and then you'd have a color image. So most of the fancy color images you see, they falsely assigned blue, green, and red to 3 wavelengths in increasing order. But unless you read the fine print, you don't know what's been mapped to the visual spectrum. In the back.
Okay, so
Hey!
hey there. So you've got you've got this very clear transition happening at redshift 7.
Yeah.
And we've talked about this in terms of, okay, this is when the ionization of the intergalactic medium is happening. In terms of the galaxies themselves, is this really representing when collisions are becoming most common? Is it representing something else about the sort of how star formation is happening within galaxies at that time? I'm trying to tie it back to the galaxy evolution here.
Yeah. I'd like to know. I think that's where we're at in the question. I mean, I think before these images, the idea was, okay, this was when filaments of gas were just kind of raining down on the galaxies. And then these pictures kind of open into question of, does it have more to do with the mergers?
With the merger process.
And you might have thought, you go look at numerical simulations of structure formation, and the two aren't even that separable, that there's streams of gas raining down, and those streams are carrying more galaxies that cause the mergers.
Okay.
Yes.
Okay. Okay.
Yeah.
I think this is more curiosity. When the globular clusters look like they kind of scattered around the core of the galaxy, are there some that are really inside as well, or is it just on the outside?
Yeah, there's some on the inside too.
Just like this one.
These pictures we're looking at now are merging galaxies, right?
Yes.
Are they rare or predominant? Like most stars we see are doubles or triples. Is that the same thing going on? And if so, is it define what your initial thing about the 2 yellow balloons and what Hubble himself told us? Is it going against dark energy and the expansion? You have to have all these close enough that gravity takes over, and instead of expanding with space, we're all going to merge into big lumps, multi-galaxies.
So you got a couple different ideas there. Let's take them one at a time. Okay. So first you said are these more common, the mergers here?
Yeah.
Okay. It looks like it. It's still being worked out. At these early times, mergers were fairly common, but it does seem like this sample, the mergers are more common than average, okay? So again, there's a hint there that the mergers have something to do with these being mononucleators. Okay, now the other part, the Hubble expansion. And are these going against the Hubble expansion? Because they're merging.
Is the Hubble expansion the same thing as dark energy?
No.
Dark energy is not making the expansion.
So the Hubble expansion
That's a separate thing.
is an expansion of the space itself.
Okay.
Think of it as that could be the surface of the balloon, okay, expanding. Whereas here, a gravity is holding the galaxy, the stars in the galaxy, their mass, distorting the space, making gravity, and that's holding them together. So, a galaxy, a star, me, you, we don't expand with the universe. We're held together. Electrostatic forces are holding my body together largely. I mean, gravity is holding the moon or the earth together, so it doesn't expand with the rest of the universe. So here, the two galaxies, the gravity is pulling them together, and instead of being, they are moving through space. As space kind of is expanding, and they are moving through space.
But in 4 million years, we're gonna merge with a big galaxy called Andromeda.
Yeah.
Or are we also gonna suck up the little orbiting in our local group? Like you mentioned, Magellanic Clouds,
Yeah.
Triangulum, they're all gonna merge with us.
Yes.
So everybody just sort of gonna become big cities.
Yeah.
It's gonna be larger voids.
That merger with Andromeda may turn us into an elliptical galaxy, produce a starburst with what gas is left.
And that's happening everywhere.
Yeah.
Well, that's good, man.
Things get boring.
I'm just kind of curious. So, like, we talk about the age of our solar system. That's pretty. What would you say? 4.6 billion years ago, or something.
Yep.
And is that because we can clearly state that the sun formed at about that time, and the common direction of the planets going around the solar system implied that they formed together from some big cloud, right? Have a common angular momentum. So I guess sometimes, when you look at a galaxy, doesn't it look like the same thing? And, why would you consider, like, is it the age of the bulbs in the middle that defines, almost like the sun would define our solar system, the age of the galaxy?
So you're saying, like, why wouldn't the
Yeah, one
disk
common
form at the same
angular
time?
momentum for the system, right?
Yeah,
That takes time
yeah.
to form, and
That's one of the things that makes it interesting, right, that the ages are different, right, that it comes in later.
no, these wouldn't have any of that, right? They're really just kind of the inner bulges of them, or?
So, we get a lot of insights in this from numerical simulations, okay, where you just program a computer to describe the laws of physics and put dark matter and baryons in it and see what happens, okay? And what happens is in the little seed particles that are dense, they grow. They keep collecting more material. So here's a galaxy that's formed, but then at much lower densities, here's gas at later times that's still streaming toward it. So, what's happening is it just continues to collect more material over time. I guess you could say, why doesn't the solar system do that? I mean, the solar system is collecting more material, it's just the angular momentum, right? It's
The
keeping it out
limited
there.
size to start with.
Yeah, I mean, and it's similar here in that material coming in later has got more angular momentum, that's why the disk is growing late. Collisions, though, are a large part of it, right? Our collision with Andromeda is gonna disrupt a lot of the angular momentum of the two systems, right? And the gas goes smack, that will lose a lot of energy and dissipate to the center. And, I think the answer to your question boils down to collisions between galaxies are much more common than collisions between stars within galaxies.
The supermassive black holes of the two galaxies will also merge.
That's how you grow supermassive black holes and then mergers. Yeah.
So one of the redshift happens because of the expansion of the universe, but there can be redshift because of the motion of the galaxies, like Doppler effect. Is there a way to tell the difference? Does the Doppler effect throw off your measurements or prediction?
Yeah, good question. Yeah, so the galaxy can be moving relative to us and make a Doppler shift, either because the space is expanding between us or because the galaxy is moving through space. The only way to separate them is when you have surveys over very large regions of space, right? And then you can use the motions of, thousands of galaxies to kind of find the center of mass in that region of the universe. And then all the galaxies, none of the galaxies are really at rest, okay? With respect, they're all moving through it. But they're moving through it at typical speeds that are hundreds of kilometers per second, or, in the richest clusters, 1,000 kilometers per second. So over very large scales, that kind of comes out. But, when we look at an individual galaxy, part of that Doppler shift is from the motion through space. It'll be of order hundreds of kilometers per second.
Folks, if we want more of this, we're gonna have to auditor class. Or go up to City College and audit Sean Kelly's class. You're teaching this stuff, aren't you?
I know not this detail, no. I'm
But we
learning.
will next semester.
You did good. I gotta tell you, you gotta be out by 9, so we got 15 more minutes to socialize, and I'm gonna give you our priceless ceramic shoebox cup.
Oh, thank you.
Come and ask a few questions on the way. We gotta be out by 9, everybody. See you next month.